Hello, my name is Yongjun Lenn. I'm a physical oceanographer at Bangor University, and that means that I study ocean circulation, currents, waves mixing, and how that all interacts with climate. So today I'm here to tell you about how the sea ice, or rather the cryosphere, the ice in the ocean and the ocean interact together and impact our climate. So I thought I'd start our talk with a little experiment that you can certainly replicate at home. And hopefully will teach you something about how our oceans work. So here we've got two simple glasses of water from the tap. I'm going to get one to be more ocean-like by adding lots of salt into it and stirring it up to mix it. So I'm going to dissolve all the salt in it. I'm just stirring it up with a little chopstick. So essentially we've got what would be a lake in this glass over here, which is just fresh water from the tap. And I can see that salt is all mostly dissolved now in this glass here. And this is going to replicate our ocean or seawater. Any one of you who's been to the beach before will know that it's pretty salty if you try and drink the ocean water as compared to when you're in a lake. Right, so what I'm going to do now, I'm going to let that settle a little bit, is add some ice to it. So here I've got ice cubes. Well, they're in the shape of fish, but that's not important. What's important is, and useful for experiment, is that I have dyed these ice cubes. They are just made from fresh water and they've just been dyed with a little bit of food coloring. I've used blue because, well, it seems like a nice ocean color. So I'm going to plonk a bunch of ice cubes in the left glass into our lake and approximately a similar amount of ice cubes into our ocean. Now I'd like you to think about which of these glasses is all the ice going to melt in first. Right, and while you're thinking about that, let me just add one more. I think it's an extra ice. There we go. That seems more even. And while you're thinking about that, let's get on with the rest of the talk I've prepared earlier. Okay, so let me share my screen. Super duper. Right, so here's the talk I prepared earlier. As I said, we're going to be talking about the ice that's in the oceans, and the ice in the oceans actually takes two forms. So here's a picture of Antarctica and the ice around it. And you can see that I've put little arrows into what look like kind of thicker areas of ice that are actually sitting out over the ocean. There's of course lots of ice and snow on top of the landmass of Antarctica itself. Let's see if I can get a little pointer. No, probably can't get a little pointer. So there's lots of ice and snow out over the land masses themselves. But then out over the ocean, you've got what is kind of a thinner layer of ice, and that is frozen seawater. You can see I've labeled that in the bottom in the light blue, whereas on the thicker layers of ice, what they are ice sheets. And ice sheets are really the extension of glaciers, and glaciers are frozen river water. So the sea ice that is around Antarctica is something that's seasonal. It grows as it gets ice forms as winter comes on, and the layer kind of expands out away from Antarctica as the season progresses, and then melts back towards Antarctica as summer comes on and melts all the sea ice. Whereas the glacial ice and the ice sheets, they're there all year round. Okay, and there's interesting things that we can think about why we are interested in keeping the ice on our planet. And this includes all the kind of both the sea ice and the glacial ice, because ice is white. And its whiteness reflects a lot of solar radiation back out to space before it can be absorbed by the ocean or land. And this helps to keep our planet temperatures comfortable for life. As you can see, it reflects about 85% of solar radiation back out to space, whereas if you had much darker land or ocean, only about 7% is reflected back out, and 93% will be absorbed by your darker ocean or land. So what has been happening to the ice on our planet as global warming has progressed over the last 50 years or so, 100 to 50 years? Well, we have slowly lost a lot of the ice. Glaciers from mountains, from Antarctica, from Greenland, have all been melting slowly. And we've also had a reduction in sea ice. This graph on the left shows you the Antarctic mass variation. So that includes both the mass of the continent, the land, as well as the mass of the ice. And since we know that the mass of the land has not really been changing, what you see in this decrease is obviously the mass of the ice on Antarctica. And it's just been going pretty much straight on down since we've been measuring it. And this is the period of the GRACE satellite that measures mass. At the same time, what you have in terms of the ice sheets and what's happening to them is that they're starting to break up as a result of the warming ocean. And you can see here in 2017, we had a big chunk breaking off the Larsen B ice sheet, which is off the Antarctic Peninsula, which is approximately, I would say, maybe a quarter the size of Wales. So a really big chunk of ice breaking off and floating out into the open ocean. Now, ice sheets float. So when they break up and melt, they don't change our sea level at all. So floating ice, as it melts, does not change sea level. However, the reason we're concerned about ice sheets breaking up is that they are the extension of the glaciers, which are the frozen rivers that sit on the land. And they help to slow the rate at which the glacier slides into the ocean. And so as we're starting to lose our ice sheets, our glaciers will start to flow into the ocean much quicker. And that glacial ice is what we're more concerned about with respect to worrying about sea level rise, because ice on land, when it melts and enters the ocean, it adds mass to the ocean and raises global sea level. So that's why we are concerned about breaking ice sheets. So how are we melting this ice? Well, of course, we have just warmer air temperatures in general, but the ocean also has a big role in melting the ice. If you think about any kind of ice, it's frozen, right? It's frozen, so it's at the freezing point of whatever, of water. But the ocean is liquid, which means it's above the freezing point of water. So the ocean is always going to be at a higher temperature than the ice. And what we know is that temperatures, or rather heat, of which temperature is just one way to measure heat, always goes from where you have a lot of heat to where you have less heat. So the ice is always going to be absorbing heat from the liquid ocean. And in Antarctica, what we're really concerned about is when we get deep, warm water from lower latitudes creeping onto the shelves. So when this deep, warm circumpolar water, as you can see here, creeps onto the shelf, if it gets up to the grounding line of where the glacier separates from the land and starts to melt it, you can start accelerating the whole glacier and melt the ice shelf above as well. And so there's a lot of interest at the moment in studying the pathways for the deep water to get up onto the shelves and slopes of the Antarctic continental shelf seas and up underneath the glaciers, as it were. So that's one way in which we're trying to understand what's going on in the kind of tidewater glacier ocean interaction system. Now let's think a little bit more about sea ice. So one place where you have primarily sea ice is the Arctic Ocean. And the Arctic Ocean does have rivers flowing into it, but not quite so many glaciers. But the whole Arctic Ocean, because it's at the North Pole of the planet, is subject to very low temperatures in winter, and it pretty much freezes right over in winter. And so the sea itself freezes over and you get 100% sea ice extent in the winter, and it drops down as we reach the kind of warmer months. So if you look at this figure here, what you can see is kind of, well, this is actually only about when you start getting the melting in about June, so on and so forth. And you can see on an annual cycle every year in June, July, the sea ice extent. So the total area of the Arctic covered by sea ice kind of drops down to a minimum that is reached in about September and creeps up again as the sea ice starts to freeze every year. And you'll notice that over the years, so these gray bands here kind of show you the sort of average that has been happening from about 1981 to 2010. And in the last 10 years, we've had all these extra lines in the bottom. In fact, this year, 2020, we reached the second lowest minimum sea ice extent in September that has ever been recorded by our satellites. And we're creeping back up again, which is good, but you know, over the last kind of 40 years, you can see that there is really an inexorable downward trend to the monthly average sea ice extent for October. And in general, that's true for all the months. And so we're really starting to lose our sea ice, and the amount of area of the Arctic Ocean covered by this reflective white layer. And that is a problem because it generates this sort of positive feedback, right? As you're starting to lose the sea ice, you get more area covered by the darker ocean below. And the darker ocean below absorbs 93% of the solar radiation, which means it stores that heat. It can come under the existing sea ice, release that heat back up to the sea ice, and melt the sea ice from below. So solar radiation can help to melt the sea ice from both above and below. And when it melts the sea ice from above, you get things like these. These are melt ponds. So below these areas of water is not, these don't connect directly to the ocean because these are ponds on top of the kind of frozen seawater, sea ice sheets in the Arctic. So these melt ponds also are act the same way an open ocean would. They're darker than the surrounding ice and snow around them, and they absorb more solar radiation, accelerating the rate at which you're getting melting of that frozen layer of sea ice on the Arctic. And this sort of explains how that happens. And, you know, it helps those kind of the solar radiation, which is absorbed, helps the ice melt more quickly. And the number of melt ponds we've had on the sea ice has increased over time quite dramatically. But we can also melt the ice from below if we can get heat from the lower latitudes. So the warmer oceans from the lower latitudes, if that water gets into the Arctic, perhaps we can melt the water from below. And indeed, that's kind of what is happening in the Arctic Ocean, because the Atlantic water from the Atlantic, so that's coming up, what you see is closest to us, it's that big red slug that represents the Atlantic water that flows into the Arctic Ocean through Fram Strait, which is between Greenland and Svalbard, and also through the Barents Sea, just south of Svalbard. And that flows into the Arctic and brings a lot of heat into the Arctic from the lower latitudes. Up to now, we would say that it hasn't contributed too much heat to melting the sea ice. And the reason for that will hopefully be obvious from the results of our experiment here. So let me stop sharing now and show you what's happened in our experiment. So in our experiment, let me stop share. Let's have a look to see what's happened here. So if you have a look at these two glasses, hopefully what you can see quite clearly is that one of these glasses, and this is our freshwater glass, has become dyed blue pretty much really well. And we'll have a look at this at the end of the experiment as well. And what that means is that this ice, as it melts and is cold water, really cold water. And cold water tends to be heavier than, well, room temperature water, and it sinks down below, bringing the room temperature water back in contact with the ice. So this sort of circulation is keeping the relatively warm room temperature water in contact with the ice, allowing it to give it heat and melt it continually. Over here in this glass, what you see is that it's not really been dyed blue nearly so much. And if you can see quite clearly, there is a layer of blue water at the top. Do you see that? There's a layer of blue water at the top, because that water, when it melts, is cold, so it would normally be heavier than the water below, but because we added salt to the water below, and the water below, the salty water below, is denser, and so that fresh water can't sink down below the denser salt water. And if it can't sink down below the denser salt water, the warm salt water doesn't stay in contact with the ice. And if it doesn't get in contact with the ice, it can't give its heat to the ice. So essentially, this layer of blue water is beginning to insulate our ice from the water below. And that indeed is what we have in the Arctic, which is why up to now, we've not had a really great big melt out, because the amount of heat that the Atlantic water brings into the Arctic is considerable and could melt all the sea ice quite rapidly in 1 or 2 years. But we have not seen that happen in 1 or 2 years because of this insulating layers in the Arctic. So let me keep sharing my screen. However, this is changing. This is changing. As you can see in the Barents Sea, which is, so I can't, where can I get a mouse? Oh, I had a mouse before. Oh, well. In the Barents Sea, which is the picture of the map here, and if you look to the top left of the map, you can see that's Svalbard. To the left is Fram Strait. And the arrows show the warm Atlantic water coming in to the Barents Sea from the left. And you can see these dashed and solid lines to the north. That is showing you how the sea ice extent has retreated in the Barents Sea over time. And what we found is that there's a big kind of correlation between the amount of sea ice. And so if you are to plot the amount of sea ice in the Barents Sea, and that's the blue line going up and down in the graph below. And what we've done there, what these scientists have done is flip the blue line for the sea ice extent, so that when it looks like it's going up, it's actually really going down. You can see it's minus area of ice. So this upward trend in the blue line is actually a decrease in the sea ice extent, but you can compare that really quite well with the increase in the red line below, which is the temperature of the Atlantic water coming into the Barents Sea. So as the ocean is warming at lower latitudes and carrying that warmth into the Arctic, that is beginning to impact more directly the structure of the water column in the Arctic, and is kind of starting to erode these layers of stratification that we see in our experiment from here, as it were, and starting to impact the ice directly. And that is something that some colleagues of ours have proven to become increasingly important over the last 10 years. So that's something we have to watch out for. So there's this whole positive feedback going on. So as we've warmed our planet by putting greenhouse gases into the environment, that extra warmth is starting to melt the sea ice. And the sea ice, or the ice in general on our planet, which we also call the cryosphere, which has been so effective at reflecting solar radiation back out to space, has reduced, which means the planet is absorbing even more heat, which helps to melt the ice faster, and so on and so forth. So as I said before, the ocean is stratified. And by stratified, I mean the ocean has layers. So if we look at this experiment here, you can hopefully clearly see that the ocean, oh, maybe I should move it here. That's right, if we look at this experiment here, you can see an example of the layers that you see in the ocean. And in general, what we have, if we were to look at a temperature section going from, say, Greenland all the way down to South America, or rather Antarctica. So Greenland's in the right side of the picture, and the Antarctica's on the left side of the picture. And going down on the y-axis is depth. And you can see a cross-section of the ocean and its temperature in this picture. And red is warm, blue is cold. Not surprisingly, red is at the top, where the ocean is more in contact with the solar radiation and can absorb heat from the sun. And blue is all the deeper waters, which are much colder. And again, you know, cold generally means denser, and so cold water tends to sink down below warm water. You can also see a similar picture of stratification from the salt content or salinity. And so here's a salinity cross-section of the ocean, and you get high salinities. So the oranges at the surface where there's high evaporation. So that takes away fresh water from the surface, leaving the salt, making it saltier. And then it's fresher down below again. But what's kind of clear is that you get really cold, relatively fresh water deeper down. And what's happening is that essentially as our planet orbits the sun and rotates on its own axis, the oceans get exposed to solar radiation at lower latitudes, store a lot of that heat and carry it to the polar regions. And when it gets to the polar regions, that warm water loses a lot of its heat to the atmosphere above, and sometimes it's involved in sea ice formation in areas called polynyas, which are areas of open water. You need open water in order for the water to lose heat to the atmosphere. And when it is able to do that, it gets really cold and can sink down below the warm water below. And essentially, on the global ocean, you have this complex system of what we call overturning. You get the warm water currents, and that's shown as the red currents, red and orange currents in these diagrams, taking all the heat from the tropics and subtropics and carrying it up to the north or way down to the south in the Southern Ocean, losing all that heat, becoming transformed, kind of taking in some of the fresh water from the melting ice and sinking down below before returning to the lower latitudes at depth. And this whole process is really important for maintaining global climate, because of course, without the Gulf Stream in the North Atlantic and the North Atlantic current extension, which you see is the kind of red current that comes past the UK and goes up into the Arctic, without those important ocean currents, the UK would be much colder than it is today. So the heat that the ocean carries in it and is able to exchange with the atmosphere at higher latitudes makes more of our planet, a wider range of latitudes, habitable. So we need the whole kind of ice ocean system to function properly in order to maintain the global overturning circulation of the oceans, and in order to maintain the kind of climate that we enjoy right now. And at the moment, as you can imagine, all this is under flux and changing with global warming. So in conclusion, I just want to finish by reminding you all that the ocean is a source of heat to the ice, and that's how it interacts with the ice. The decline in ice sheets and sea ice really show that the polar oceans are responding much quicker to climate change than any other parts of the planet. And this is a problem because this will eventually impact all of us. And I should say that if you're interested in research, the processes that transfer the heat from the warm water to the ice continue to be really important topics for research and is something that we're all fascinated by. And despite being far away from most of us, the polar oceans are really important parts of how you experience climate and weather. So thank you very much for listening. I hope you learned something exciting and have lots of questions to ask later. Right, so that's all from me for now, and I will catch you in the question and answer session later on.